Oh, good. So yeah, just let me start. And actually, this topic will be a little bit different, but will provide another perspective on battery manufacturing. And yes, as already introduced, my name is Sebastian Thiede. I'm a professor of manufacturing systems at the University of Twente. Large parts of this work, or at least the studies that I presented in this work, are also related to my previous position, which was at the Technische Universität in Braunschweig, so the battery lab factory there. So some colleagues I mentioned here, but of course, there are a lot of other colleagues were involved over the time, like Artem Turecki, Arno Quadro, Christoph Herrmann. I think, if I saw it right, Artem is also here in this event. So what I would like to do is to provide, two different perspectives on battery manufacturing, and these are on digitalization and sustainability. And furthermore, I want to have a closer look what are the interdependencies and synergies of those two topics. So as I said, my background is the University of Twente in the Netherlands. So we just in the last year, we brought together all the competencies in our Twente Center for Advanced Battery Technology. I don't want to present all the details here, obviously, but within that, we deal with different stages of the life cycle, especially going towards next generation batteries. And my role is there to coordinate the activities in the advanced battery manufacturing. But let's come to the contents. And as I said, there are two different perspectives. And the one perspective I'm dealing with today is sustainability in manufacturing. And in general, not just related to battery, obviously, manufacturing has, unfortunately, a very high share on the global environmental impacts. About 30%, even more actually, of the CO2 emissions worldwide are caused by industrial manufacturing with all the different aspects. So this is certainly one thing that we need to address for the future. And that's why I also put a focus on that here in this presentation. But the second one is certainly the issue of digitalization in manufacturing. And you can name it Industry 4.0, smart manufacturing, industrial Ethernet, whatever you want to say there. In any case, I think we agree that there is a significant progress in information and communication technology. And the question is, how can we bring that together? And this is exactly the point and some leading questions for my presentation today. How are digitalization and sustainability aspects are connected in context of battery manufacturing, obviously? And related to that, of course, can digital solutions contribute to sustainability? Again, of course, in context of battery manufacturing. So in the next minutes, 30, 40 minutes, I want to go through the following agenda, give you some introduction, some background that I think is necessary to understand the later case studies, but also the setting that we are dealing with here. Then some general framework, actually more technical framework, which is relevant for the later case studies for both of them. And then I picked out two examples. One is dealing with machine learning for material efficiency, and the second one is machine learning for energy efficiency, before I close with a summary and an outlook. So let's directly come to the introduction. And we all know that, and that's why we're dealing with batteries, or at least that's a strong driver behind that, that in the end, for the example of cars, there should be an environmental benefit out of that. So of course, the overall idea is, now sticking to the example of cars, that we have an environmental break even over the lifetime, so there is less CO2 emissions, for example, over the lifetime of an electric vehicle, compared to a conventional vehicle with internal combustion engine. But also the typical challenge that we face here is that electric vehicles cause higher environmental impacts, and as we all know, also higher costs in the production phase. So we have this backpack that we have to overcome over the life cycle. And that's why we have to have a closer look into the details here. And if you do that, again, without going into all the details at this point, we see, of course, that the battery plays a major role in this whole thing. So 40–50% of this environmental impact is caused by the battery, and more particular, even the battery cell is a major driver for that. And typically, if you look into studies, and there's just a very recent one that was published by Volkswagen and the German Engineering Association, you see it's just another case study that underlines that the manufacturing of electric vehicles compared to conventional ICE vehicles is a factor of 1.5 to 2 higher. And of course, the idea is to overcome that over the use phase and be in total then environmentally more beneficial. And by the way, a very similar story could be told from the economic perspective, of course, because also in terms of costs, the battery plays an important role. So, okay, so far so good. We all know that that's the playing field that we are in. So the general question is, what can we do about that? And I want to make it just one slide excursus to in general industrial value chains. So what are the fields of action that we can distinguish here? And if you look at a typical value chain or the different sectors that are connected to industrial manufacturing, you can typically distinguish between 3 different elements. On the one hand side, you have, of course, the mining, where everything starts, mining the iron ore, whatever. Then you have the materials industry, and typically you talk about the big 5 here, steel, aluminum, chemical, cement, and paper. And then you have the manufacturing of your semi-finished or finished products. And what's interesting to see, if you take a look now on the share of these different sectors on the primary energy demand, it looks like that, right? So you have here 10 to 15% for mining, 10 to 15%, depending on the study, for the, let's say, discrete manufacturing of your finished products. But you have a large share on the material side of things. 70 to 80% of the energy demand are caused here. And why do I tell you that? And by the way, this is, of course, just the perspective cradle to gate. So I'm leaving out here the perspective of the use phase and the end of life to some extent. What does it mean now in terms of the measures that we could take? Actually, there are 3 different ways to deal with that now. On the one hand side, we can, of course, improve the material efficiency. So everything what we can save in terms of materials will reduce the upstream energy demand, and also with that, of course, the related environmental impact. So what can we do? We can avoid the waste. We can increase the quality rate, and I will come to that in more detail. We can better utilize the material, or we can improve the recycling. But please also note on the same side that also in the material industry, and of course also in the other sectors, energy demand is still a very relevant topic. In the end, it's all about energy, right? So improving energy efficiency as the ratio of output to input is a very important topic as well. So selecting efficient technologies, dimension it or control it in a proper way. And last but not least, of course, a very powerful third strategy is substitution. We all know that. So that is relevant for both energy and materials. So switching to sources which are, for example, renewable for energy, or at least that cause less environmental impact through the value chain. So far, so good. This was a little excursus, but the question is, what about battery manufacturing? So what are the relations there and the relevance of those different strategies? And if you take a look again into an economic environmental assessment, and you all know those figures, and this is just one study I picked out here in terms of costs for battery manufacturing, it typically looks like that. You found numbers between 60 to 75% of the costs are related to the material, right? So this is by far the most important point. And behind that, you have quite a share or different portions, let's say, that have a similar share in terms of the relevance on cost. And energy, here the red one is among them. So it's by far cost-wise not the most important one, but still a very important field and in similar order of magnitude like others. But let's have a look also on the environmental side of things. And this is yeah, it's a little bit older from Ellingson, but still I like that overview from the environmental impact and the different impact categories that are related to that. So what you see here in the lines are different environmental impact categories. Typically most popular and well known, the global warming potential, so contribution to climate change. If you look into that, and again, this is cradle to gate, of course, leaving out the use phase, you see pretty well this blue part here. This is the manufacturing of the battery cells, more specifically the energy demand. So in terms of the global warming, global warming potential was right. There is quite a significant influence of the energy demand of production. If it comes to other impact categories, I don't go through all of those. You see also that other portions play a role here, and typically most relevant, you can say, yeah, as I said, the manufacturing of the cells. the negative current collector, so the copper, and the positive electrode paste that plays an important role here. With depends now on the different impact categories that you look at. I have listed them here. Again, that really is depending on what you're looking at. So this is an interesting insight already, how the different aspects in terms of materials and energy play together. And of course, now we want to understand a little bit deeper, what does it mean for battery manufacturing? As we all know, battery manufacturing is a quite complex thing, right? There are a diversity of different processes, quite specialized, very interdisciplinary, very important, right? You have process engineering, you have discrete manufacturing, you have electrical engineering. All these things come together and typically within a factory, right? So again, you have there from production technology quite some challenges to bring together batch or continuous production with discrete manufacturing over the whole process chain. You have a strong influence, and that needs to be incorporated, as you will see, in the so-called technical building services, which are relevant or responsible for providing the environmental conditions. And we all know that dry room is a very important thing in battery manufacturing, but also other things like compressed air or obvious things like lighting and so on. So we have to take this into account, and this leads to quite a complex system with different interactions, conflicting issues that need to be incorporated. And I have not even talked about the different inputs in terms of different materials, different cell types and design and so on. And in the end, you have even a lot of different properties you want to have with the battery in the end, right? And those are just examples that are shown here, like energy or power density, safety, of course, cost, and so on and so forth. So how to bring that together? And with that, I want to jump to this point of the digital solution. So everyone is talking about digitalization, what it's all about. And I think one key concept behind that is the aspect of so-called cyber-physical systems. And if you name it like that or in a different way, fair enough, that's fine. But what's important to understand that, of course, it's a system of different, with different components, different elements that need to be considered. Yes, in the end, we want to improve the physical world. This is what we want to change, right? We have certain design and control parameters and certain state and influencing variables. And yes, we like models. Being a researcher, I like different models, right? Physical, database models, whatever. So fair enough, that's good. But here in the sense of digitalization, we want to bring them together with data gathering, continuous data gathering. So we need proper strategies for that. We need to identify what are actually the data streams which are most relevant and bring them into the virtual or cyber model, as it's said here, cyber world, in order to have an up-to-date model that can be used on two ways. On the one hand side, it can provide decision support for the different stakeholders in such a factory, or it can even be embedded in a control. And as an addition to that, I want to emphasize that digitalization, or just putting things in the computer and connecting things, is certainly not Industry 4.0 or smart manufacturing. This is just digitalization. And I like this figure from the colleagues from Aachen that presented it like this with the different maturity levels, right? Of course, this is a prerequisite for all the other things. You need to have your things digital. Things need to be connected, either locally or even through the internet. But then it gets more interesting when it comes to those different steps. So understanding or seeing what's actually happening, this is the first step, right? Gaining more transparency, understanding what's actually happening, what are the root causes of certain behavioral patterns. Then predict even what will happen in the future. Can I be working with scenarios, and then how can I influence that in a positive way? And last but not least, of course, how can the system even adapt itself, even on an autonomous way? So these are the different stages. And when we talk about those different digital solutions, and I will present some of them in the following slides. So where can we locate them, and what is their contribution? Because in the end, yes, the value is increasing as well when you go from left to the right, the potential benefit, but also the effort is increasing. And the question is, of course, what is the right balance there? So if you bring that now together in a certain framework, and for me that also brings together the different aspects of digitalization and sustainability in general, and of course also for battery manufacturing, you can say, okay, on the one hand side, we have here the different levels, maturity levels or capabilities of digital solutions. But then we have to take into account the different levels of the factory, so production processes, building service, and the factory system as a whole. So this leads to a different combination of measures, so you can fill out all of the boxes or could stand for different solutions that play a role there, either in planning or operation. And then last but not least, very important, the different fields of action come into play. And there provide different perspectives on the same thing. And it's important also to incorporate the interdependencies in between, as you will see in the examples. And this is the energy and material efficiency and the substitution. So I just want to use this framework to allocate some of the solutions and want to go a little bit deeper, of course, in two of those. So again, some examples for energy efficiency. I leave out the gray ones here just more for your orientation and some background. Of course, there are solutions can be found also outside of battery manufacturing on different levels, on different maturity degree and so on. But I will focus today in context of energy efficiency on energy efficiency measures through applying machine learning in context of battery manufacturing, obviously. The other ones are also interesting, how to bring that together. By the way, this example here for factory simulations also in context of battery manufacturing. And there's also quite some interesting work on dry room optimization based on digital methods, but that's just not the focus for today. The second example is dealing with material efficiency. And I really like one aspect here, and this is the aspect of quality management. Because typically quality management is perceived as something, of course, a standard thing that you do in factories when you operate your factory. It's very important. Process capabilities, ramping up your production in a state where you produce robust and with high quality rate. That's an important thing from technical and economic perspective. But on the same side, or the different perspective on the same coin, if you want so, is also that it's very important, as you saw before, for the sustainability, for the environmental sustainability. So I want to focus on that as well. Whereas again, also the other issues have at least some indirect contribution to battery manufacturing as well, but this is just not the focus for time reasons. So what is the general framework related to that? So what I mean with that, what is the technical background? What are the issues that are relevant for both the case studies that I'm dealing with? So as I said, not too surprising, we built it up as a cyber-physical system. So in the end, what we dealt with is really having a look at the physical world in the sense of the battery manufacturing process chain. I don't need to explain you, obviously, the different steps here from electrode production up to the cell assembly and formation. And very important, I will stress that even more in some moments, are the different elements here, or the different types of variables that we distinguish here, because in the end, of course, for us, it's important to understand the relationship between the process, resulting structures, and the final properties then of your intermediate products or your final products, so the battery cells. So I will show one example how the data acquisition was realized without going into technical details. Then, of course, very interesting, the virtual world, what kind of models are used here. And for today's presentation, I will focus on just data-based or machine learning-oriented models, on multivariate regression, neural networks, and actually also random forest. And as I said, those could be used for both decision support and control. Whereas a lot of challenges have to be solved there. And these case studies that I will show you are based on, as I said before, on the infrastructure of the battery lab factory Braunschweig. Maybe some of you know that, or I'm sure some of you know that, where the whole process chain is there is available on industrial scale machines, as you can see here. And in this case, I will always refer back to this typically pouch battery cell that you can see here with a 15 electrode separator, 15 compartments that are realized here for achieving around 9 ampere hours. The first step was, of course, and we published that some time ago already, is to understand what's actually there, right? And so what we created is this landscape, this overview, this map of the different data streams that are available. Of course, I can just give you a little bit of an insight and can just refer here to the publications about that. So what are the different steps, of course? What are the relevant process parameters? What can be analyzed? Is that offline? Is that online? What are state variables, and what can be learn from the different steps here. So that was done in a structured way. And all together, and I want to stress that a bit because I will use the terms quite frequently, we distinguish between these different aspects here. So, of course, we have an input coming in, then we have a process, and in the process you have certain parameters and also certain state variables that occur. Process parameter, of course, could be the line speed in coating, for example, or calendering, or some specific things that you parameterize there. But the state variables are occurring things like a power demand, or maybe even vibrations or noise that occurs, so things like that. Then it results, of course, in what we call intermediate product features, IPFs. So this is important to investigate what is the outcome of the specific step. So that could be structural properties like average particle diameters, in general, intermediate product characteristics, connectivity, for example. And then in the end, it's about the FPPs, as we call it, the final product properties, right? And this is in the end the battery cell and the determining factors or final properties of the battery cell. In this case studies, we considered hundreds of different parameters and state variables, as well as intermediate product features, and distinguished between 65 different final product properties, whereas I will focus on just very selected ones, obviously, in this context. And of course, the question of those kind of data-based analysis is now, how do they interact? What are the influences? What are interdependencies? And how can we work with that? Yeah, just a few words to the technical setup. You can read that in the publications. So what's important to mention that we distinguish between automated data acquisition and manual data acquisition. So automated, obviously, everything that you can get out of your machines or from different sensors, or even some things from the technical building services. This is all brought together automatically in a manufacturing execution system, or actually SCADA system. But it's combined as well in the data warehouse with manual data. For example, if you have your final product, or actually also intermediate product analytics, you might even use some simulation data and so on. So things that are more triggered manually or acquired manually. But of course, you need to bring that together, synchronize that to be finally stored, and then be applicable for machine learning and data mining based approaches. But let's come to the examples. And the first one is dealing with material efficiency. And I kind of introduced that already a bit, what we call virtual quality management. I think that's a very interesting point because it brings together the economic as well as the environmental perspective. So as we know, improving the quality rate is still considered as to be one of the grand challenges in battery manufacturing. Of course, it's a sensitive issue. Not too many numbers are available, and very early one, of course, from some years ago, talked about scrap rates from 5 to 12% in studies. What I hear, it's not that unrealistic still. So of course, it's a very crucial issue, especially having in mind the high share of material on the battery cost. And as you also saw from environmental perspective, it's also very important. Additionally, it's important to note that the most valuable and critical materials, for example, the cathode, they are already used in an early stage of the process chain, obviously. So it's even more important to avoid quality problems later on, because you would lose the whole cell with everything what happened already, all the energy you put in, all the material put in. So we took a process chain approach here to investigate what will happen over the whole process chain. And yeah, for material efficiency, I don't go through all the points here. Of course, there are some benefit. We want to identify the critical parameters to improve the quality that can be used in either planning or control of such process chains. And the idea is to use what we call soft sensoring here, soft sensor approaches. So you want to predict certain quality properties without actually measuring it. So we want to use data which is there anyway, maybe like from the machines or other state variables or intermediate product features, and use machine learning based models to predict the quality properties. And in the end, this is of course very beneficial. It could be high degree of quality transparency, but still with a reasonable effort. And on the other side, you can even use that at stages where quality checks are hardly possible or applicable just for technical reasons, for example, after the electrolyte filling and so on, where you have quite some effort to measure, for example, every cell. So now what are the data or the variables that we distinguished here in terms of the final product properties? As I said, we started with 65 different properties there, but here are just some variables. In the next examples, I will focus on maximal capacity as an example, and also to some extent on formation loss. So this is actually what we're targeting at, obviously. And the first step was now to identify over the whole process chain, or actually in this approach through variations in 3 different steps, namely calendering, laser cutting, and Z-folding. We investigated, first of all, the influence on selected FPPs, as you can see here in the different lines. And so we did, of course, variations. And here, this is just a one-way analysis of variance. This is important to mention. So it allows us at least to identify what are significant influencing factors. And it's quite interesting to see, if you just take a look here at the heat map, is that some of the things are just related to one process step. Others, so FPPs, others are related to different processes. For example, the capacity is related here to quite an amount of different processing steps. And also it shows just examples here that laser cutting has quite some interdependencies here, this one, with a variety of different FPPs, which is quite interesting. So far, so good, but that does not really help for what we actually want to do. That just gives you an indication about the possible significance, but still, of course, it's not possible to have a continuous calculation, and also the interrelations are not that well visible. So obviously then we went into more details with the machine learning approach. I will just click through that here. Of course, the usual steps that you take there, you transform your data, you clean your data, you select your features that are most interesting. You do the model training and validation. We took a 5-fold cross-validation here. And in the end, of course, you want to have a model. I know that was very quick, but I think it's more about the results here. So in the end, you can get out something like that. And this is for the maximal capacity. What you see here on the left-hand side are the predictions. And you see that fits quite well, that you so can predict based on different intermediate product features or process parameters, the resulting final product property, in this case, the capacity. And what's interesting here is that you have this now with this process chain perspective. So you have different inputs from mixing, calendering, laser cutting, and packaging. Again, without going in all the details. And we tried different methods for that. Here are the results of multivariate regression, as you can already see, which has the advantage of relatively easy applicability and transparency what's happening. So the explainability of those models is typically a bit better. And it leads to reasonable prediction quality. Even nowadays with other models, this is a little bit higher. So, of course, this is just one perspective on that. So we brought it together from different FPPs, different final product properties. And here we distinguish again capacity, also the capacity loss after 400 cycles, and the formation loss after first cycle. And what you can see here, it's a quite complex figure, but over the process chain and the variations that we did, you see the influences now, the influencing factors on those different final product properties, as noted down here by the different colors. But of course, it's important to show, okay, is that relevant? So if you want, so the coefficient from the regression high, so that might mean, okay, this seems to be relevant. But of course, you have also to investigate whether this is also statistically backed up. So is that really statistically significant, or just the effect of whatever kind of measuring campaign that you did there? So we brought it together in this figure here with the p-value to just underline as well, okay, is that relevant and significant? So this is typically what you see here in the sector 1 here in the bottom. And it's very important, I think, to identify obviously the relevant factors, but also, for example, identify aspects here in, for example, in section 2 here, which might be interesting, so high coefficient from the regression, but the p-value is relatively high. So that might mean, okay, I should back it up with more data, more measurements, and maybe It proves to be very significant, maybe not. So it's important and gives you some indication where to focus on next. So obviously, here are some examples that I picked out here. In this case, line load, temperature were very important, the position accuracy of the, in this case, Z-folding process, and also particle diameter related aspects played a role. So this can be now used, and this is just an intro, a short overview on that, for example, in the operation of your process chain, for example, for the quality control. So what you see here is the concept of the virtual quality gates. It's also published in a paper with all the details. So the idea behind that is, of course, now that you can, at any given stage of the process chain, you can make this analysis. You can already predict with this model what is now the final product properties according for the different criteria. And of course, with that, you can now say, okay, is that now still in a range that I wanted to have, or is there some deviation? And of course, then the question is what to do with that. Maybe I need to adapt then the parameters, for example, at the next step, that might allow me to bring my final product properties back in the corridor, right? And of course, now with this data-based understanding and with this model, this might be possible, even usable in operation. I come to some discussion points in the summary and outlook. Of course, there are some challenges related to that. But however, this is an aspect that could work quite well. The other thing is to use it in planning. And again, now you can use it the other way around. Maybe you want to have certain final product properties, and you can now relate it back to the necessary IPFs, so intermediate product features, and process parameters, and then derive a necessary setting of your process chain. You can then use process or process chain simulation as shown here, or maybe again use machine learning based predictions to indicate and to estimate what should be your process parameters and your necessary intermediate product features. So it's a little bit the other way around. You fix the final product properties and derive the necessary parameters for the previous steps. As a second example, I want to come to the aspect of energy efficiency. And yeah, I introduced that as well. So energy demand is very relevant when it comes to environmental impacts, especially for the global warming potential, but it depends also very much on the scale of production and the battery types. A very often cited and shown picture is that one. It's very interesting actually to see. Was just published in a recent paper as well from our Norwegian colleagues. I think they're also here in the meeting, and which just shows the energy demand of production, so kilowatt hours per kilowatt of cell. And you see quite an effect over the factory capacity, the annual capacity of production. Not too surprising, many publications came out over the last years dealing with, let's say, laboratory environment or pilot lines and so on. But what you also see that they have, of course, this economies of scale. If you want, so after a certain size here, 1 to 2 gigawatt hours, it goes into a certain area with some uncertainty actually of, let's say, 40 to 60 kilowatt hours per kilowatt hours in the cell. However, very interesting to see. And of course, the question is, how can we now deal with this topic of energy efficiency? A deeper look into the battery cell manufacturing when it comes to energy demand. There are quite some studies now in the meantime, as you saw. Some go a little bit deeper and show the different hotspots. Of course, there's a broad variety of numbers that you can find. That's really orders of magnitude in between, as you also see here, right? And this is, of course, depending on the scale, on the type of production process, on the different battery variants, chemistries, and so on that are used. However, there's a certain consensus that definitely the dry room, as you see here, and let's say drying processes in general are very important, especially here in the coating and drying of the electrodes, and also in the drying later in the cell assembly. So still, there's not too much work on dealing with energy efficiency measures in battery manufacturing. There's some analysis, but what that means, how can we improve that? That's not too much, at least. So let's take a deeper look into that. So there's what we came up with some time ago is a procedure how to systematically derive relevant factors for energy efficiency. And again, I don't go through all the details here, but what's important to know is that it starts with a black box situation again. So you don't necessarily need detailed process knowledge, which is often the advantage of such kind of machine learning models. On the other side, it's also a challenge, of course. So we start, what we of course need, is the energy data, so related to time or a specific product. So if you go through the steps that I will not do in detail, you have several supporting methods that allow the systematic identification of potentials. And what's more important even, that this whole procedure that we now go here through manually, if you want, so can of course be automated and can be used also potentially for a continuous decision support or control.
You have 5 minutes left, Sebastian.
Yeah, that's fine. Perfect. So what we did is, first of all, you can use so-called energy portfolio to prioritize the machines in the factory. So you actually split between power and time and see the contributions of the different machines. And then you can use that and of course select the most relevant machine and identify for this machine what are the most relevant energy states, machine states of this machine. We used Gaussian mixture modeling for that. So you see the amount of states or power values over that you can see here as a histogram, and you can identify pretty well the different states of the machine. And we want to focus on the most relevant state then, and identify the most influencing factors for that. So, for example, if your machine is working, so full working mode, what are the influencing factors then? How can we predict that? And what can we use in terms of models to determine the impact on time, energy demand, costs, and impact? So directly coming to the case study, so we went through this. So of course, the energy prioritization, not too surprising at this point, showed, of course, that the coating and drying process is one of the very relevant ones. So this Gaussian mixture modeling was applied to identify the most relevant machine states that you can see here. You see this blue one here, cluster 5, as we called it, is has a average power, let's say, compared, but occurs a lot of times. So it's somehow interesting to further investigate what happens there. You could do the same, of course, for the other clusters here as well. So we went into that and applied the machine learning model. In total, 85 variables were used in the first stage for that. So these were process parameters, different state variables, and things that I mentioned before. So could be temperatures, ventilation settings, and so on. Of course, some scaling, transformation, and so on, and synchronizing with the energy data. And we used 3 different models here. I went over that pretty fast, but regressions, neural networks, and random forest to evaluate what's possible. Or what is equality, and it turned out that the accuracy was pretty high for all of them actually, right? So high R-square values here. So, and also we could bring it down to 10 variables that are of most relevance. You see here the comparison of the real data and the prediction, and just intuitively it looks pretty nice, as also be proved by the statistical values. So of course, now this can be used to do sensitivity analysis. So we varied those parameters, and this could be things like the surface temperature, like the specific dryer settings, you have the set temperature, or even very specific parameters in the control or the rotating speed. And based on these models, we can now identify what is the influence on the power demand. And you also see, well, without going into the details, the different behavior of the models, right? So random forest has more, that's, this different steps here. It's more like a classification method, whereas regressions, of course, and neural networks have a more continuous behavior here, which makes it maybe more applicable. But anyway, we just used it, in this case, the artificial neural network, to now predict also what are the potential savings when varying those influencing factors. And we said, for this sensitivity analysis, we just change it by 5%, either high or low, depending on the type of parameter. And what you see is quite interesting. It gives you potential energy savings, and that could be up to 9% with just a variation of 5%. You could save up to 9% per factor. And if you would aggregate that, which is of course not correct, you could say, okay, there could be even savings of over 30%. Obviously, there are interactions, so that could be not fully achievable. That doesn't make sense. But still, it's an interesting range of 10 to 30% with, remember, just the variations of 5%. So that could be interesting to take a look. And as I said, those are aspects that could be also embedded. His model could be also embedded in a direct control. So let me close quickly. Yeah, you saw a couple of different approaches, and what's important that either the material side as well as the energy side both play an important role also for sustainability. You have to bring it into an overall framework like a cyber-physical production system with all the different components to bring it to life also on a continuous way. But very important, and we all know that, of course, and this I just want to mention that proactively. Of course, these are black box approaches, and those are based on phenomena and not necessarily backed up by physical models. So there might be even misleading actions. There are some things which appear to be like that, but in the end, there might be other root causes. So we have to be careful with that. So ideally, especially being a researcher, of course, that should be a starting point, but we should work deeper and have a knowledge-based understanding of the things. And even more, these multi-criterial decisions are very important. For example, in this energy demand study that I just showed before, we left out the impacts on, for example, the quality of a product. Of course, this should not be neglected, so this should be brought together. And last but not least, we should see, is that actually beneficial to do that on a continuous way? Or can we actually achieve most of the improvement through just single temporal measurements and just do it? Or do we really need this continuous application? So further work should be done on that. And with that, I want to close and thank you for your attention. And obviously, I'm happy to answer questions.
Many thanks, Sebastian, for this very nice and very interesting presentation. So, which shows also the importance of, also dealing with the larger scale, right? The machinery scale on the manufacturing process. I think that the research work that we are doing in the artistic and what you are doing, so it's very complementary, because in artistic side, so we are really more in the physics side, right? Trying to understand, developing models to predict the influence of manufacturing parameters on the electrostructure and so on, right? So while also taking into account the machinery is very important, because at the end, so we are talking about the process, right? And we really need to optimize the energy consumption, the CO2 fingerprint, and so on. And yes, definitely it's very, very great. Thank you. Thank you for your talk. So I think, Fernando, so yes, maybe you can go ahead with the questions. We have Scott here online as well, but we still have some minutes before the next talk.
Very interesting presentation, yes. Sebastian. So I have some questions of my own. So I would like to ask you, for instance, about your models when you make multivariate regression. I assume those models are linear. I saw sometimes in your plots. And my question to you would be, do you think it's important in the future, or it would be a good idea maybe to explore including more complex model where you can consider nonlinear relationships between the different parameters?
Yes, of course. That should be actually the case. And of course, with the neural networks, for example, we went in this direction of more, let's say, complex models as well. So yes, the answer is yes. But what I actually like is still in the regression as well as the explainability, right? That you have a better tangible results, if you want so, and can better interpret this. Whereas, as we all know, with ANN, it's sometimes a little bit difficult. Of course, it's possible. We all know that as well. But still, it's not that accessible. And that's why we, especially for this first study, we intentionally actually went to this point of regression. Yeah.
I see. Fantastic.
I will pick a question here from Mark. So, yes, on slide 36, you present the evaluation of the coefficients p-values from your regression model. So do you focus on penalized regressions in order to optimize the feature selections of your model, or at least to have a comparison point? Yeah.
No, this is really, I'm not sure whether I got the question now right, but no, this is really directly the values out of the regression, and of course the separate statistical analysis in terms of the p-value. So there's no certain specific aspect and some kind of weighting factor or something, if that's meant here, included. it's a little bit now the point, we leave it at this point to the user, right? To say, okay, the interpretation is necessary without a question, but what we want to avoid is, and we all know that this happens very quickly, that you see, okay, there is a nice coefficient, there seems to be an influence, but so far so good. But you need to back it up also, yeah, with the data, so you have to see whether this is really significant as well. And this is just the idea behind it. But there was no specific method, let's say, to deal with that on a mathematical way, let's say. It's more a graphical solution, if you want so.
Great. So there's another question now from Yingwei Yin. So who is nice to see you, Yingwei, here. So she's going to be a speaker also later in this week. So thank you for the great talk. In the real production environment, due to the quality control, the collected data may lack of diversity. So would you mind to comment on this point and suggest some solutions?
Yeah, that's really an issue. We are very aware of that, right? And I really fully agree. So in this research environment, even that was a problem, is because of course there is also a batch kind of production, right? And within that, you want to produce a certain amount of batteries and keep the other things stable, but you need, of course, to have variations, otherwise you won't see any effects, right? And so you have this little problem there. And that's also where I think there could be a combination of, let's say, physical models and machine learning-based models could play a role, right? That you, to some extent, but yeah, in the end, you have this issue, that's no question. If you have really a stable production, where then you might have the effect that you cannot read out too much from your data. However, what we saw in industrial practice in some cases is that there is indeed some variety, and especially in the cases that I have in mind now that I cannot mention, but intentionally that there were some variations done also in industry to investigate those things, right? So, but yeah, I fully agree with this point. So it's really a challenge.
Thank you very much, Sebastian. I think we need to move forward to the last speaker of today's session. It was wonderful having you here in this webinar series. Thank you very much once again for having accepted the invitation and for the great talk.
Thank you very much.
You can answer the other questions in the chat, okay, directly. So I think there are plenty now that are arriving. So yeah.
Oh yeah, okay. I will have a look. Yeah, thank you.
Thank you very much.